Warning: this material has been copied or communicated to you by or on behalf of the University of Western Sydney pursuant to Part VA or VB of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further copying or communication of this material by you may be subject of copyright protection under the Act.
Okay, there you are. Go. Do it. So first step, classify it. What sort of differential equation is it? Give me all the words you can think of that describe it. Non-homogeneous. Good. Third order. Euler-Cauchy. Beg pardon? Linear. Beautiful. Yes. Ordinary differential equation. Good. So as soon as you see that it's Euler-Cauchy, what does that x bigger than 0 flag for you? You don't need the absolute values in the final answer. Okay? And as soon as you think it's Euler-Cauchy, what method do you think of? The auxiliary equation, yes, which is the M method. Good. And as soon as you think then it's non-homogeneous, you have two methods to find a particular solution. Either undetermined coefficients, but immediately you think Euler-Cauchy, no, can't use undetermined coefficients, because that's only for constant coefficient case. So the only other method that you have is the variation of parameters. Good. So that's, now it's the third order case. So where do we go from there? So your first step is going to be find the homogeneous solution. So that's what you're looking at with the M method. Hopefully you already have written that down. And because we can already solve these homogeneous ones, I'll give you the rest of the working because you've seen this often enough now, this particular example with the factors to be the 1, 2 and 3. But from there, write down what the homogeneous solution is. Have the 1, 2 and 3 homogeneous solution. YH equals. And the only reason computers are on is because you're following our work here, isn't it? Yes? Good. Is that true? Yes? The only reason the computer's on is because you're following the work here? Good. Both of you? Beautiful. Good. Okay, well, hopefully you've all written the homogeneous solution down. Very easy. In this case, it's not exponentials, it's powers. So that was, for the non-homogeneous case, that was the first step. And then for the second step, don't write this equation down. This is just to, you have it in your final exam equations, the full version, but for the third order version, the y1, the y2, the y3 come from the powers, and then we have to figure out these bits and pieces. So we also need to know the R function. What's the R function? Can you write down the R function? What will the R function be? That's the right-hand side function, so it's 2x, isn't it? Yes or no? No. Good. Because for variation of parameters, we must put the differential equation in standard linear form, okay, which means dividing through by the x cubed. So the R function is 2x divided by x cubed, which is 2 over x squared. Okay, so that's very important. Otherwise, you just won't get these integrals correct. Okay? So very important to get the correct R function because the equation must be in standard linear form. So we're calling y1, y2, y3 these things. And then that means that we need to figure out the determinants that go along with there. The Wronskian you get from writing the functions across and writing their derivatives underneath. I'll give you the answer there, so that's just something for you to check. And then figure out how you would get W1, W2, W3. See that all it is W1 is this same thing with the first column replaced, W2 is with the second column replaced, and W3 is with the third column replaced. Now I'll give you those, but you need to check that you can get at least the W1, W2, W3 efficiently. So for instance, for the W1, you would say the best way to do this is to expand it using this first column. So that's a plus minus a plus. And then, so with 0 times something plus 0, minus 0 times something, plus 1 times what's left when you get rid of this column and this row. So it's this determinant of these 4 items in there. So you need to check that you can get each of those. If you end up with a minus sign difference here, then check that you've used the minus signs through properly to the 1 there, etc. Or they're expanding this out by the third column. Okay, so that's, you have to be able to do these. Check that you can do each of those determinants. Even this first determinant is not too hard. Use this column here. It has 2 parts, but it's not too hard. Okay, so then we need to build up the particular solution. So using the formula that we have there, that's the y1, that's the y2, that's the y3. Notice that everything else in these integrals is always the same. So that's a little check. That's the dividing by the Wronskian and multiplying by the correct R function in each of those things. So they're not too hard to build up. And then the only other part is what you get from W1, W2, W3. And then where are you going to make mistakes in all of this? You're not going to make mistakes because you don't understand the theory. You're not going to make mistakes because you haven't got the right formula. You're going to make mistakes because of about year 8 fractions with powers. Okay? So that's where you need to make sure you don't make mistakes multiplying and dividing by powers of x. Once we get those things out, you need to check that you put all of that together correctly. Check that, do it without looking at this working. Do it on a separate piece of paper without looking at the working. Figure it all out and then check whether you got these answers here, which simplifies down to that. So that's the particular solution. What do you do once you have the particular solution? To get the general solution, add it to the homogeneous solution. So there we have it. There. That's the homogeneous. That's the particular. And then we ask, well, is there anything, can that be simplified at all? And it will be able to be simplified if there are things in the particular solution that are already covered by one of the constants here. You see that this is a constant times x. We already have a constant times x, and so it can be simplified slightly. And just so that you see what's happening, the difference is, instead of a C1, there's a C4 here. I haven't just lost this term on the end. C4 is C1 plus 3 on 2. Okay. Well, you know, being as, you know, maths is about beauty as well as accuracy. You know, you might lose a half a mark for not being beautiful enough in your answers. There. I would take a half mark off. Yes. All right, well, do these higher differential equations have any applications? Of course, the answer is yes. we usually, if y represents a displacement, then the derivative of y physically represents what? Y's displacement, y dot is, if y is distance, then y dot is speed. If y is displacement, remember is a vector rather than a scalar. So the derivative of displacement is velocity, okay, which is a vector technically rather than a scalar. Speed is a scalar. Speed is the size of the velocity, but velocity has size and direction, okay? And then the derivative of velocity, so the second derivative of y is acceleration. Now, you can obviously keep going, and if you have an acceleration that's changing, you see velocity changing is acceleration, but if you have an acceleration that's changing, then that's the next derivative. And you could have a change in the change of acceleration, which is the next. So you could have all sorts of later derivatives. It's just that physically, we generally have a good understanding of where we are, how fast we're going, and the fact that we're accelerating, because that is involved with a force. Okay? But if the force is changing, then that acceleration is changing, so it has a derivative as well. All right? So you can have differential equations that involve higher and higher and higher derivatives, depending on what sort of system it is that you're investigating. Now, in particular, this system comes from an engineering context where you're dealing with materials. We're going to look at the way a beam bends under a load. Now, once again, the differential equation model that we come out, will that be a true or false model? Not a good question. Good. Excellent. Okay. Will it be a useful model or a not so useful model? Well, it depends on how closely the system that we're looking at agrees with the assumptions that we've built into this model. Okay? So let's have a look at it. We have a beam of some length L, and we're going to call downwards y, and along this way will be x. Okay? And we're only going to think of a two-dimensional flexing. And so downwards positive, the further it flexes downwards, the bigger y will be. So it's a bit like the mass on the spring downwards was counted as positive as well. And so when you load that beam, this beam is sort of clearly being supported at one end or the other, so it hasn't moved. But when you load the beam, it tends to flex in the middle. And so the sort of assumptions that we're going to build into this is it is not flexing too far. Because obviously if you flex it too far, it's either going to break, there will be a stage where it breaks. And also, not flexing it too far means that we'll be able to use a few other approximations along the way. So this curve that you get here, which isn't necessarily always just uniform like that, particularly if you weighted it much more heavily on one side compared to the other side, or put some sort of force, a larger force here, then it wouldn't necessarily be a symmetric curve. And that's called a deflection curve or an elastic curve. We're assuming that the material itself is homogeneous, that is, it itself has the same density and consistency and material all the way through. So homogeneous in this sense just means the same. So certainly not all beams will be uniquely the same all the way through. If there was some sort of fault in the beam, then this model wouldn't necessarily be a good model of that system. Okay. So it could be steel, it could be wood, and it's a uniform cross-section. It's the same cross-section all the way along here. It doesn't have to be rectangular, but if it was circular, it was the same circular cross-section all the way along there, as long as it's uniform. Okay, now this is where we end up making some assumptions. Assuming that the bending is small, so that the deflection and its derivative aren't too big, so what that's saying back here is that this distance down here isn't too big, whatever too big means, but in some sense, and also the derivative. Now, if this deflection isn't too big, you could, even if it was sort of just came down a little bit, it could be a very steep slope, in some situation. If you really, 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 did something well, but we don't want that either. So that we don't want this distance down too big, and we don't want any big slopes in here as well. So that mathematically is y, which is the distance down, and its derivative, which is the slope of the deflection curve at any point, aren't too big at any particular point. It turns out that if that's the case, then the bending moment is basically proportional to the second derivative. Now you can look up what bending moment is in better terms. We don't really need to know about what that is here. But what this is saying is bending moment has to do with second derivative. And on a graph, what does second derivative tell us? First derivative tells us height of the graph. Zeroth derivative tells us distance up on the graph or down on the graph. First derivative tells us slope of the graph. Second derivative tells us rate of change of slope. There's a geometrical term that I'm looking for. Yes, if it's equal to 0, but points of deflection are where what changes? Concavity, that's it. Okay, so yeah, point of deflection, point of inflection, concavity. So basically what this is telling me is that the bending moment graphically has to do with concavity. You know, something's concave up or something's concave down. We have this idea concave up is a cup, concave down is the other way around. And the constants of proportionality, for various engineering reasons, it's useful to have a thing called Young's modulus and the moment of inertia. And the moment of inertia has to do with that cross-section as well of the beam. And for that to be, if the cross-section is constant, then the moment of inertia is constant as well. Okay, so that's what we're talking about here. We can also, from theory, show that the second derivative of the bending moment has to do with the force, the load per unit length. If it's under gravity, then if you load it, then it's being pulled down by gravity. Okay. So how do we get a differential equation out of that? Well, it's not too hard, because if I'm talking about second derivative here, and I take the second derivative here, what's the second derivative of a constant times a second derivative? Well, that second derivative turns into if you differentiate the second derivative twice, you get the fourth derivative. Okay? So what this is saying is that the second derivative of m is this same constant times the second derivative of y. And the second derivative of y is the fourth derivative. The second derivative of the second derivative, sorry, is the fourth derivative. So there we have a fairly simple higher order differential equation. It says that a constant times the fourth derivative is the load per unit length of this beam, according to some assumptions. So that's a model. Hopefully, if we apply it in a situation that agrees with the assumptions that we've made for the model, then it will give us some reasonable answers. All right. Now, what else can happen? Not only do we have this sort of situation happening with the fourth derivative, the actual beam itself could be supported in various ways. It could be what's called simply supported, that is, you just put like a point at one end and a point at the other end. So if you started loading this down in the middle here, you would expect the whole thing, the point at the end of the beam, to start sort of bending upwards. And the further you load it, the more it would bend upwards. Now you see there's even a slight assumption built in here, because technically, if these bearing points here were right on the extreme very end, as soon as you put any weight down in the middle and the beam bent up a little bit, what would happen? It would fall through, because the bending up of the beam, you haven't lengthened the beam, bending up means it must have got shorter in a horizontal sense. So there's a slight assumption built in there that you haven't actually put it exactly finely right on the very, very end, so that any loading means that it comes in short. So by loading, we're ignoring any decreases in length in the beam, any horizontal decreases in length. So we're sort of almost assuming it actually stretches to stay on the bearing points. Okay, so that's the first little assumption that happens there. Now, when it's simply supported, what that means is that the height y at x equals 0 is here. If I just simply support it there and I put a load in here, does that height change at all? That's what the support's doing. It's keeping it at the same height. And the same at the other end. So we have this idea that y is equal to 0, at x equals 0, that's there, and also at the other end of the beam, x is equal to L. So that's two pieces of information in this case, we have y is 0 when x is 0 and x is L. Another way of writing that would be y at 0 equals 0 and y at L equals 0. That's another way of writing those two pieces of information. It turns out that by not clamping these or doing anything else, the concavity doesn't change at those endpoints as well. And so that's what we mean by the second derivative at 0 being 0, and the second derivative at the other end also being 0. The concavity stays at 0. It's not that it doesn't change, sorry, that it stays actually 0 at that last end there. Okay, now think about what that is. If we were told the beam was simply supported, a fourth order differential equation would give us how many unknown constants in the general solution? 4, okay, because you basically have to integrate 4 times and you get a constant integration there. And there we have, if we were told it was simply supported, we have 4 pieces of information, which would then allow us to somehow calculate each of those 4 constants. So that's good. What if it's clamped at both ends? Now you can see the difference. If it's clamped at both ends, still the height hasn't changed when you start loading it up here. But what happens to this? You can see here the slope at these ends is actually changing. The more you load it, the bigger the curve becomes and the bigger the curve here happens. But what happens if it's clamped is that the slope always stays the same at the clamping points. Which in this case, you still have the height is being maintained the same. So when x is equal to 0 and when L is equal to 0, the height is being kept at 0. But now instead of the concavity staying at 0, clamping it means the slope of the beam stays at 0. So once again, we get, instead of the double dash there, it would be a dashed in each of those cases. But it would still be 4 pieces of information that will allow us to calculate the 4 arbitrary constants. Now, the other case is, what if it's only clamped at one end? Would that work? Well, we'd call that a diving board, wouldn't we? If it's clamped at one end and free at the other, the more we load this up, the further down it's going to bend. Turns out that we get the same, they're called initial or boundary conditions in this case, at the left-hand side. So we had y equals 0. So this is saying y, when x is 0, y is equal to 0, is that case. And the derivative is there, so that's the clamping that matches with the previous case. It turns out on the other end, though, that at x equals L, the second derivative is equal to 0. So that's sort of like the simply supported case back up here. But in this case, where there is also no support there, turns out that the third derivative is equal to 0. The third derivative has to do with shear forces that are to do with internal horizontal forces of the beam, and it turns out that in that case the shear forces are 0 at this end. Now there are other combinations. You could have clamped and simply supported at one end or the other end as well. You could have not clamped horizontally. You could have one or other end clamped at a different angle, which would just mean instead of the derivative being 0, the derivative was some other slope. Okay? You could have not clamped at the same heights. So one could be clamped here and one could be clamped down here, or not simply supported at the same heights. Okay? So they would be different. So instead of y equal to 0, y might be some other height. Okay? Now, probably what you couldn't have is simply supported at one end and free at the other. Why not? Because the whole thing would just fall off, wouldn't it, in that case? So there are some that aren't, some combinations that aren't practical. But there are further extensions of this that you could have simply by making some minor changes to these details. Well, let's go ahead and solve this case. There's our higher order differential equation, fourth order. If I divide through, and what we're saying here is that in this case we're just going to have a constant load. So looking at here, we're putting the same mass per unit length all the way along here. So there's a constant load. So we would expect a symmetrical solution. The answer would be different if it was under gravity on the Earth compared to gravity on the moon. If we were talking about putting constant masses here, but if we're loading it in a constant way, that means we're applying the same force. So if you took the system up to the moon, you'd have to increase the mass sitting on there by 6 to apply the same force per unit length. Okay? So if that's a constant, F naught, we divide through by these two constants, we basically end up with a very simple differential equation. The fourth derivative is equal to a constant, and we could go back to our original units by using these details. So if I said the fourth derivative was equal to 2, what would the third derivative be? This is an x derivative, 2x plus some constant of integration, wouldn't it? Okay. So this doesn't involve any lambda methods or whatever. It certainly is a linear constant coefficient non-homogeneous differential equation, but it's a very simple one that we don't have to go to any of these other methods for. We can just integrate step by step. Okay? So in this case, instead of it being a 2, it's a constant. Integral of a constant is a constant times x plus a constant. Go from the third derivative to the second derivative. The integral of x is x squared on 2. So the constant just stays the same there. The integral of this constant is constant times x, plus what else do we have to add on? Another constant from the indefinite integration. Okay? Now at this stage, if it's simply supported, we know we're dealing with that first case. And the idea with the first case is that where you start being able to use some of these equations is when we get to the second derivative. So we've integrated far enough up to get to the second derivative, and it's a good idea to get rid of these constants or figure out what they are as soon as we can. So here is where we can. We know that when x is 0, the second derivative is 0, so let's put 0 in there, 0 in there, 0 in there. I end up with C2 equals 0. So that's pretty easy. What about at the other end? That will involve, wherever there's an x, putting L and the second derivative on the left-hand side there being 0. So I'll have a 0 there, an L squared and an L there, and I don't have to worry about that anymore because we already know that that's equal to 0. So there's what we have there, and that is one equation for C1, which means I could subtract that from both sides, divide through by the L, and this gives me this. Why can I divide through by the L? Normally I would have to write L not equal to 0, but I know that L physically represents, what does L represent? The length of the beam, doesn't it? So I know I'm not going to be interested in a 0 beam length. Okay, so I know it's not equal to 0 because it's the length of the beam. So that's not equal to 0 physically, not mathematically, but from physical considerations. Now I can look at this, and what that means is when I substitute the C1 back up into here, I can get this. You check that you could do the algebra to get that. So that simplified everything down to a situation where I have no unknown constants. Remember, K comes from the physical problem and L is the length of the beam, so everything is known there at this stage. Well, can I go further? Well, certainly I can go from the second derivative to the first derivative by integrating and then integrating again. So here's another thing that you need to check, that you could go from there to there integrating twice, and each time you integrate you get an extra constant. So that's from the first integration and that's from the last integration to get here. Well, do we know anything else? Well, yes we do, because it's simply supported. We know that when x is 0, y is 0. So let's put a 0, 0, 0 in there. Means, and with y is equal to 0, C4 must be equal to 0. So you need to either, you can see that now or you can check that out. And the alternative at the other end is that when x is L, that is, put an L there and an L there and an L there, you still end up with 0. Plugging it all in equal to 0 gives you an equation for C3. And so we know that that's 0, and we know that that is this function here of L, and so that's what we end up with. Okay? Now, yeah, that's, you say, well, so what? Okay, well, I could do a couple of things. I could put the constant back in terms of the original bits and pieces. There's a common factor of 6 that I can take outside. would leave me with this, but in fact there's also a common factor of x through there, which I can take out, and that would leave me with a cubic, and being left with a cubic, you might also notice that you could factor out this term here as well. Now that makes a lot of sense. The form of this makes a lot of sense because we expect, for this simply supported case, that the height when x is 0, that is at the left-hand side of the beam, the height should be 0. And is it true, when I put 0 in there, that I get 0 for y? Yeah, because 0 times anything is 0. All right? But we also expect that the height when x is at the other end of the beam, when x is equal to L, that height should be 0. And this shows us that immediately, rather than having to substitute it in there. If I put x equal to L there, what do I get? L minus L, 0. 0 times anything, still 0. So that tells me that this makes a lot of sense. In this case, I've drawn this graph with L equal to 1. This is x. This is the positive direction for y. And for some reasonable values of f0 and e and I, we get this sort of deflection curve when you graph this. Okay, so this is the way that the beam has bent under a uniform load. Okay, forming y like this. Any questions? All right, now again, there was nothing particularly difficult in going from this very simple fourth order differential equation. The hard part is knowing which of these to use and to put in, and doing each of the integrals and the bit of algebra where you calculate the constants correctly. All right? Other than that, easy. Any questions? Will this be in the exam? Probably, possibly. Can't tell. Yes, question? If you look in the exam formulae, you get these things. At least I used to. I'm pretty sure you still do. So just check that in the formula. Okay. Well, no other questions. You have at least 6 hours plus the extra 20 minutes of this lesson to work outside of class on this. But certainly, if anybody wants to see me now for any other questions, please do.
See, this is a thing called anotype. You can use your own PC, right? So that's a laptop. Anyway, if you press this button here, press the annotate button, you can use the pen.
Ah, right.
But I don't know if it's going to work.
Oh, right.
Once you're into your system, then you just go back to this laptop. So.
Oh, okay.
So,
Yeah. I just turn it while I've set it up. I turn it to there.
oh, you can use that?
No. See you next time. Hi. Thanks very much. What's that?
Still recording for this lecture, so
Oh, okay. Somebody with.
get it there and just put.